All right, welcome everyone. So today we're talking about generative models. So what does generative models mean? These are models that can actually create stuff in the world and actually model the world, not just discriminate, but actually generate. So we're going to look at two of the most popular models out there. So generative adversarial networks and variational autoencoders. And more broadly, we're going to talk about how do models learn representations. And I have an awesome set of people to thank for the slides. So they're listed here and they will be listed on every slide. So we basically have seen the concept of representation learning. So when we talked about convolutional neural networks, we talked about the distinction between the traditional classical fully connected neural networks in blue and the modern deep learning addition in red. And the point that I made at the convolutional neural network lecture was that the big advance came here. Namely, we knew about this since the 60s. We knew about sort of fully connected networks, and that was nice and beautiful, and we had a gazillion parameters that we could learn. And if all of these were fully linear, then it wasn't any better than a single layer linear model. But the moment that we introduced nonlinearities, these were amazingly powerful and able to learn very cool functions. But the true innovation of deep learning came from this part here on the left. Namely, when we discussed convolutional neural networks, we talked about this classification task as more or less an excuse for learning representations about the world. And that most of the power of the model was coming from learning the convolution of filters themselves, which at the lowest level were learning about edges and then corners and then, wheels and dashboards and cars and more general scenes and so on and so forth. So that's where a lot of the power and advance came. And the rest, you can just plug and play. But the representation learning and the feature extraction was what I highlighted as perhaps the most important concept in convolutional neural networks. And in fact, it's the same thing that's pervasive in recurrent neural networks, in graph neural networks, in all of these autoencoders, the variational autoencoders, the adversarial networks, all of these things are all about representation learning. So that's the key pervasive idea that I wanted to get out of this course and more generally of machine learning. The concept that the classification task was in fact driving a feature extraction task. And the feature extraction was where all of the knowledge representation of the world was coming from. And that is in fact an extremely powerful and general paradigm. And I was like, be creative. The field is still at its infancy. There's many application domains beyond images that have structure that current architectures do not yet capture and exploit. So as you start thinking about representation learning, this is the place to be very innovative about your own architectures. And again, in genomics and biology and neuroscience, you can actually use the application domain areas to develop potentially new architectures. And that's what I think the project could be all about. How do we both take existing architectures, but in some cases, can we expand beyond the existing architectures to learn some representations about the real world? What I want to do in this last sort of machine learning focused lecture of the class before we dive into the application domain is go into generative models and namely get rid of this. Just put a big X there and basically say, do we really need classification? Do we really need labels? Namely, the exciting part in my view was the Z, was this latent space representation. And we had an X, which was a bunch of data, and we had a Y, which was a bunch of labels, and we were, distinguishing images of cats versus boats. How exciting is that? Well, yeah, it's kind of cute and it's exciting because you can watch pictures of cats all days and never get mistaken by a boat, and it's wonderful. But the most important part is that it was actually learning a model of the world. And therefore, the big question is, yeah, great. There's millions of labeled images out there with Ys. But what if we forgo the why altogether? Then there are many, many orders of magnitudes of more data where we can actually learn Z's without actually knowing any Y's. Okay. So the goal today is going to be, how can we get rid of Y and just focus on learning representations in all kinds of other cool ways? So who's with me so far? Everybody can see sort of the, the point that we're trying to get at here with representation learning. So wonderful. So 189100. So the reason why this is exciting is because suddenly we can use self-supervised learning. This is not quite the same as unsupervised learning. Unsupervised learning basically says, find some cluster in these data. But self-supervised learning says, I'm going to make some classification tasks or some prediction tasks or some supervised task by exploiting just the data and tricking the data into being its own supervisor. So it's not quite unsupervised, but it's not quite supervised either. It's self-supervised, where you're using part of the data as training for other part of the data with the explicit goal of learning very cool representations. And why are representations cool? Because you can use representations to generate views of the world. You can basically run the model backwards and basically say, given a latent space representation, given a set of vectors that basically tells me, I see headlights and I see a rotational pose and I see, an older person, etc. Can I vary these vectors and then generate images by basically going backwards through this architecture and then having expansions of these compressed representation of the world into examples of the world? So that's what the generative models are going to do, running the model backwards and effectively going from Z to more examples of X. Okay. So in the context of recurrent neural networks, we saw one example of using self-supervision as a way to learn representations. And the self-supervision was constantly predicting what's next in the world, basically using the time series nature of, speech data or of video data or any kind of input that we're receiving from the world, using the temporal aspect of that as a way to learn a representation that captures something meaningful about the world and then predicts the next item. So in video or in speech or in any kind of textual, you can actually predict the future. Everybody with me on sort of the relationship between CNNs and the concept of building representations through future instance prediction, and then suddenly have all of the training in the world you want, because every day, all day, you're learning from supervised examples. You're constantly saying, oh, is the world sort of behaving the way that I would have expected? And if not, you're surprised. This whole peekaboo of a child. The child basically has a view of the world where the peekaboo sort of surprises the world. And suddenly the moment you close your face and you reopen, there's a unexpected thing that's happening in the world. And that's sort of the excitement of the prediction. So we're at 55, 35, 603. All right. So that's predicting the future, recurrent neural networks, and then video. Another very, very cool idea is pretext tasks. We don't really care about, the task at hand. All we care about is that the task is giving us an excuse to learn representations. So one example of that is predicting self. And that's what autoencoders are all about. You're basically saying, great, can I have a compressed representation of the world that allows me to just repredict the same original image? So that's a pretext task. No one actually cares about predicting the image itself. You already have the image. But the concept of going through a compressed representation and then re-expanding into the image itself through a clamp is in fact meaningful enough that you can actually learn a representation underlying the world. So we're going to dive a lot into autoencoders and then see variations of that into variational autoencoders that explicitly model the variance and the distributions of these models. So that's one example of predicting self. Another example is predicting between two images, which image came before the other one. If you see a person shooting a goal and then the ball is further down, the only way to predict that the picture with the ball entering the goal, the ball entering the goal, is that you have some model of physics, you have some model of movement, you have some model of causality. So predicting before and after is extremely difficult unless you actually understand the world, and that forces you to learn these latent representations. Another example is you remove a patch from an image, and then you try to predict the missing patch. You basically give the image an input, which is the image without the missing patch, and then a y vector, which is coming from the x, but with the patch, without the removed patch, in other words, the original image. So basically, x is now the image without the patch, and then y is the original image. And you're trying to predict the remaining pixels of an image. So that, again, can't happen unless you have some representation of the world. Or you rotate an image and you try to predict the correct rotation. Again, who cares about that task? But the trick is that it's tricking you to learn latent representations. Or you give a black and white, you take an original image, part of your data, you put that original image as the y, and now you have a training example with a label, which is the y, which is the original image. And then as the x, you create a black and white version of that image. And that colorization task, again, forces you to learn representations of the world. Or you could take an image, downsample it, use the upsampled version as the y, and use the downsampled version as the x, and then force yourself to effectively learn representations of the world on the way to predicting that image. Or, connecting sound and video. So all of these tasks are pretext tasks. You don't really care about the task at hand. You are constructing, you're tricking the input data that has no labels to become a self-supervised task by splitting that original image, transforming it, making that transformation your x, and making the original image the y, and then using that to create a supervised learning task. All right, so who's with me so far on this second concept of pretext tasks? All right, so we're at 55, 45, 00. Okay, so the other thing is, who feels that they've already learned something? I've only shown you the outline, but who feels that they're already like, wow, this is a cool concept. Awesome, very cool. Lots of people are learning. This is great. I always have my biggest fan of one all the way at the bottom. One person, maybe a different one each time, maybe the same one. But we're at 50, 35, 13, 0, and then one person. Nope, I really still don't see why the professor's all excited. Okay, so let's dive right in. So we're going to first look at pretext tasks, then we're going to look at autoencoders, then we're going to look at variational autoencoders, then we're going to dive into generative adversarial networks, and then again, the sky's the limit after that. Okay, pretext tasks. So the goal is you have some input signal, and then you're processing that signal through your network to effectively learn representations of the network. And in the end, you're using your input signal to create a training signal, some kind of pretext task that you really don't care about. So basically, you process the image, and then that processed image is the input to your network. So for example, I can remove a patch in the processing, or I can make it black and white, or I can downsample it. And in the end, that input signal goes into the training as the thing that you're trying to predict. But you don't really care to predict that, you already have it. What you care about is the representation learning that happens in the middle. Okay, so that's basically the concept of self-supervised learning. The goal is to learn good representations, and the means is to construct a pretext task that you don't really care about, but it enables you to do learning. And therefore, you can get so much more training data than if you have to restrict yourself to places where people have actually labeled it. There's only millions of those, but there's billions and trillions of those. So you know, yes, millions is a lot, but nowhere near enough to learn complex representation of the whole world for the machines that we're building. So some pretext tasks are, for example, inferring the structure of an image. You basically break the image into patches, and then you learn where do the different patches go. It takes an enormous amount of conceptualization to do that. And that's why that task is actually quite useful. Or a transformation. You're scaling or distorting or rotating an image, and then you're trying to recover the original image, which again has some concept about the world. Or exploiting time, or using multiple images in multiple modes, and so on and so forth. And again, these are a very rough classification of tasks. And then some tasks that in fact fit many categories. And you only have to pick one or multiple concurrent similar methods. And you know, if some task is presented before another, that doesn't necessarily mean that it was invented before. So here's one concept of inferring the structure of the image. So you basically cut 9 patches from your image, and then your task is this patch next to this one, or to that one, or to that one, or to that one? So basically, what is the relative position of those tasks? So if you basically, if I give you an image of this and an image of that, and I tell you which one's above, to below, or to the left, or to the right, then you guys have some concept of the world. So as you're watching this, you can see that this is the top of the bus and this is the middle of the bus. So, you know, chances are that this is, you know, above that one. Or if I show you, you know, pictures of tracks and wheels and pictures of trees and, you know, the top of a train, you can sort of figure out which goes where relative to each other. So if the network is able to recognize the relative relationship with, again, a ton of training data that is labeled because I constructed it from unlabeled data, the best way to do that is to actually recognize the objects at hand. So again, you give these to a network and then a classifier that decides where they go. So this was the first self-supervised method, and it's a very intuitive task that should enable learning about object parts. But on the downside, it assumes that the training images are photographed with canonical orientations. The training is on patches, but you're trying to learn an image representation. And then again, the networks can kind of cheat. So you don't want the network to simply learn that there's, you know, more blue in the sky in general, and that's sort of more likely to be up. You want to sort of, you know, force it to learn actual true representations without, quote unquote, cheating. And it's not quite fine-grained enough because there's really no negatives from other images. And the output space is actually only, you know, 8 positions to distinguish from. So it's actually fairly limited. So jigsaw puzzles are another example where you now not only need to decide what is the relative orientation of 2 patches, but you have to actually reconstruct the original image. So I give you this and you have to figure out that, you know, the general arrangement is that one. Another one, which is actually surprisingly simple, is you do a simple rotation. You basically take an image and you rotate it. And then you try to have the network predict the original rotation of that image. It sounds very silly, but it works amazingly well, and it actually forces the networks to learn views of the world. And again, this is much easier if you actually recognize the content, and therefore the machines end up learning concepts about the world. So again, the pros is that it's very simple to interpret and use and quite effective. And the cons is that it assumes that, again, once more, the training images are photographed with canonical orientations, that there's no rotated images and, you know, no fine grain resolution, and so on and so forth. Okay. So another example of a pretext task is I, you know, skew or scale or stretch or, you know, transform my image in some way. And then you have to figure out the inverse transformation. And again, you have an encoder, a decoder, you have to learn a representation of the world in order to be able to do that. Another one is to remove a patch of an image. And again, you have the why, which comes from the original image. You basically take your original image, you treat that as the Y, as the target prediction, and then as the X, you mess it up in some way by removing a patch. And then the goal is, can I figure out the missing patch? And again, the goal is that you mask out a portion, you have an encoder, and then the decoder has to have some explicit representation of the world. Another kind of cool thing is coloring images. You take a colored image, you transform it into a black and white image, and then you have the network trained on gazillions of these pairs, where you basically now are learning something about the objects as an intermediate for actually coloring those objects. So another one is, for example, you could have a vocabulary of visual annotations for these words. You could have all kinds of examples of instances where you're trying to classify examples from your image representation. So all of these are, building the same kind of concept of pretext tasks. I encourage you to go through slides where you can sort of see just the diversity of examples applied to these. Another example I mentioned earlier is multimodal, where you basically are watching a person play the guitar or play the drums, and you have a sound output, and you're trying to match the two to each other. And some of these pretext tasks can be helpful by themselves. Coloring images can actually be a nice perk that you get on the side, but the goal was always to learn a latent space representation. Okay, so who feels that they've learned something here so far? All right, 55, 40, 006. Okay, so this is, the first type of representation. So you're basically creating these pretext tasks, and then you're trying to learn a representation of the world that will make you solve these seemingly complex tasks by actually learning something interesting about the world. As I mentioned, the earliest, perhaps, view of all these was a pretext task where you're actually trying to predict the self from the self by going through a clamp. And then that clamp is, in fact, the representation. So you can think of this as taking the red, flipping it around, and then expanding it back out through a compressed representation of the world. Okay? And that's what autoencoders are about. So basically, the concept is you have some input data, X. You're trying to extract some features. You're trying to encode X into a lower dimensional representation. And then you're trying to use X to predict, you're trying to use that lower dimensional representation Z to predict X all over again. So it's an unsupervised approach for learning lower dimensional feature representations from unlabeled training data. So you're turning an unsupervised learning task into a supervised learning task. So the Z is usually much smaller than the X. So there's some dimensionality reduction. And the goal of clamping down your network, so you only have very little information that can flow through the middle of the network, is to force meaningful representations of the variation of your data. Because if there is no clamp, then you can just simply predict every pixel. But if there's a clamp, you're forcing the network to actually learn something meaningful. So originally, this was just a linear and some sigmoid functions. And then later on, it became, coupled with deep learning and fully connected layers and ReLUs and convolutional neural networks, etc. So the goal is from the features, you then seek to construct X hat, which is the decoded version of your encoded. And then your goal is how well is X hat capturing the original X. So the loss function is simply the difference between the original and the predicted. And you can use, for example, a 4-layer convolutional filter for the clamping, basically 4-layer convolutional filter for your encoder, and then a 4-layer up convolutional, which is basically taking smaller representations and then expanding them out into, edges and shapes and pixels ultimately. Okay. So who's with me so far on the autoencoders? So the goal is, again, you're taking your input, you're clamping it through a middle layer that has very little information flowing through, and then you're using that as a way to predict ultimately an output feature. Lovely. Okay, so 70, 25, 5, 0, 0. Okay, now here's what's kind of cool. We basically were thinking about just building representations of the world, and Z is a representation of the world. But here's what's very cool. I have actually created a generator function. I can use my Z to construct images from the world. I can vary the Z and then construct different images. And what's really cool is that the Z is actually in a meaningful space. The Z might actually tell me about the relative features and the presence of different features in the world that I'm actually able to use to generate additional images of the world. So, I can throw away the encoder, or I can throw away the decoder, and I can use different parts of the network. I can basically say, how well can I tune this to capture different aspects of the world? So I can have a generative model here, and I can just have a representation learning model there. So both parts of the model can be helpful. I can throw away this and have a generator. I can throw away that and have a representation learner. Okay. So, and the encoder can be used to initialize now a supervised model. So basically, I can have either a generator, or I can throw away this part, and I can actually have a representation learner. And this is actually very helpful, even with GANs and with all kinds of other features that we're going to see, and all kinds of advanced machine learning. Having an autoencoder is wonderful because it gives you a meaningful feature space, a meaningful projection of your data into a lower dimensional space where you can actually carry out all of these operations. So who's with me so far on sort of how I can use the encoder or the decoder separately for different tasks? I can use the decoder just as a generative model. I can use the encoder as a feature space vector representation learning that I can then use to compare how similar are different images to each other, or to use them to find, either variations of different images, to do projections, and so on and so forth. All right, so 70, 25, 5, 0, 0. Cool. So here we are. We talked about pretext tasks. We talked about we talked about autoencoders of predicting the self through the clamp. And now let's dive into variational autoencoders, or VAEs, which again have been extremely useful and extremely powerful in many ways. So the concept of a variational autoencoder is effectively a probabilistic spin on autoencoders that lets us sample from the model to generate additional data. Okay, so in this Z vector, initially, Z was static. It didn't tell us anything about how much that varies. But the concept of a variational autoencoder is that we're now going to have not just the mean, but also the variance of these vectors. So basically, we're learning from a multidimensional representation a set of scalars. And for every scalar, I'm going to have an associated variance. So for a vector of scalars that I've learned, I'm now going to have the variance associated with each of those. So we're assuming that the training data is generated from an underlying, unobservable, latent representation. And then we're going to be sampling from the true conditional distribution of generating this is the decoder part of generating images from the underlying latent representations. So we're going to be sampling from the true prior of those latent space vector, and then we're going to generate images from that. So again, X is an image, Z is the latent factors that were used to generate the image. These are various attributes of the image. For example, is this a man or a woman? Is this an old person or a young person? Does that person wear glasses or no glasses? Are they tanned or not? And so on and so forth. Are they facing to the left or to the right? Are they happy or are they sad? So all of these vectors should be tuned in a way that they best capture the world. That's the only goal of the autoencoder. But as a byproduct, they end up being meaningful representations of the world, where if I vary these parameters, I can actually get instances of different images sampled from those parameters. Okay? So I can basically sample from that conditional and sample from the prior, and then use that decoder network to effectively generate additional images. So we want to estimate the true parameters of this generative model. And we can represent the model by choosing some prior distribution for Z, for example, some Gaussian. And then we can have the conditional P of X given G be as complex as we would like. We would like to be able to generate an image from that distribution, where if I vary my Z, I can basically get a variation of those images. And then I can represent that through a neural network. So the strategy for training the generative models is to learn the model parameters to maximize the likelihood of the training data. And now we're going to basically look at the probability distribution over the learned parameters of my model, over the theta of my decoder network, of the images from the world X. And these images are going to be sampled from the prior distribution. This is a very simple Gaussian. And now the cool part here is this deep neural network is generating those images from the X. And then I'm integrating that over all possible Z's. And then I get a more meaningful distribution of the possible images from the world, whereas the space of all possible pixels on an image is enormous. The space of all possible real world images is dramatically reduced. Okay? So everybody with me about sort of how I'm now sampling the set of images from the underlying distribution of latent vectors rather than from the underlying distribution of pixels, which can be enormous. And that's sort of, you know, a very cool feature of these networks. Okay, so 25, 52, 12, 12, 0. So the problem, of course, with this is that this is actually an intractable distribution. So basically, you know, this is just an enormous space and it's very hard to sample over it. So what we're going to do with variational autoencoders is probabilistically generate these models by explicitly modeling both the mean and the variance. And this is going to be just a diagonal covariance matrix. So every vector is going to have just a single vector rather than a full covariance matrix, a vector of variances with a one-to-one mapping between every latent scalar and the corresponding variance of that scalar. So basically, our decoder network is going to start from the set of possible latent space vectors and then generate images from that or generate data in the real world. And this could be genomic data, audio data, image data, you know, any kind of data about the real world. And we're going to have both the mean and the diagonal covariance of these X given Z. So basically, these are the images that can be sampled from the underlying distribution. And then here I'm going to also have a diagonal covariance of what are all the possible encodings of this image in the Z space. And then we're going to be, you know, probabilistically sampling these from an underlying distribution. The beauty of having the encoder have not just a single Z, but a variance of the Z, is that I can now sample X's from a normal distribution, and I can sample, you know, latent representations, and similarly, I can sample X's and Z's. So we can basically think about those as, first of all, a recognition or an inference component which is basically saying, given a bunch of pixels, I'm recognizing a boat and some variation about the boat. And a generation network, which basically says, given that I know that there's a boat, it has a length, it has a scale, it has a size and orientation, etc., I'm generating images from that underlying representation. So you can basically derive the probability of generating those images. This is the distribution of images. And you can derive that from just the, just taking the log of this. And then there's an expectation from that, which is coming from that Z distribution. And then you can use Bayes' rule, as we had seen before, to basically express this over the conditional probability. So X given Z times P of Z divided by Z given X. So you're replacing this with the corresponding item from Bayes' rule. And then you can just multiply out the constants with all of this. And you can transform this into three components, basically three expectations based on your latent space. And then you can actually represent those into, this is nothing but the KL divergence. This is the difference between the two distributions of the original Z prior that you have, and then the encoder space representation of Z from X's. And then this is the KL divergence of the exact converse. Basically, this is the decoder and the encoder on both directions, okay? So the first term is effectively the decoder network giving you the probability of your images given your latent space and all of the parameters of the neural network that transform between the two. And you can compute an estimate of this term by sampling. You can sample and you can use a reparameterization trick that I'm going to point you to later on for doing this sampling. The second term is this KL term between Gaussians of the encoder and the original prior. So that's the encoder, that's the original prior. And this has a very nice closed form solution that you can actually sample through. And then this term here is actually intractable. So just like we saw earlier, this is the same term here, and we can't compute this KL divergent term. But the beauty of it is that because this is a plus sign, and we know that KL divergence between distributions is always positive, we can treat this function as a lower bound. We know that this data likelihood, the probability of observing the data given our model parameters theta, is going to be at least this term plus some, additional positive term. Okay, you don't have to worry about all of the math, but you can definitely, look it up. But the beauty of all this is that we have a tractable lower bound, which we can take the gradient of and which we can optimize. And this P of X given Z is actually differentiable, and the KL term is differentiable. And then we have an intractable term, which is always going to be positive. And the beauty of all that is that as I'm training my network, this discrepancy between these two is going to be getting smaller, but that is going to be done through gradient descent and through improving the parameters theta of my network, of my encoder and of my decoder phi. And all of these are going to be effectively improved through examples, okay? As for these two terms that are actually differentiable, we're going to be using this variational lower bound, which is going to be the loss function of my set of images, and then the two parameters of my encoder and decoder network. And this is going to be how well can we reconstruct the input data. And the second part is going to be how well can we approximate the prior distribution of images using this decoder network that is basically giving us this encoder network that's giving us the Z from the X. Okay, so we're going to be maximizing the lower bound here, and then we're going to be minimizing the error term here. Okay, so putting it all together, we're going to be using our input data to model not just an X, but both a mean Z and the variance of every Z. And using that to sample, rather than have a single Z for every image, we're going to be now sampling from the explicitly modeled mean and variance of this data. And then using Z, we're not going to be generating a single X, but we're going to be generating a mean and a standard deviation, which we're going to be again sampling from to generate samples. So we're going to be maximizing the likelihood of the original input being constructed as one term, and we're going to be maximizing the similarity of that posterior distribution and how close it is to our prior. And for every mini match of input data, we're going to be computing a forward pass and then backpropping through all of this. So again, we've now turned unsupervised, I have a bunch of X's, into a supervised network that is basically trying to model a representation of the world through not just a mean, but also a variance for these latent variables, Z, and their corresponding factors. All right, so let's see who feels that they've learned something. Okay, so we're at 41, 48, 4, 0, and 7. So how do we now use this in a meaningful way? So I can basically decide to encode all of my images of pixels in the MNIST dataset that you did your first problem set on. I can encode all of that using only 2 dimensions in my latent space. I can basically say, well, I don't want to learn an 8x8 pixel and 64 dimensional vector. What I want to learn is just a 2-dimensional vector that is going to allow me to construct all digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, using only 2 dimensions. So I have Z1 and Z2. So I've now forced my variation autoencoder to capture the space of all possible characters into only 2 dimensions. And again, this is not possible if your images were random. These are real images from handwritten characters. But now I can vary along the Z1 and the Z2 vectors, and I can generate any kind of character from this. And any kind of character that I see, any kind of image, is going to be represented using just a 2-dimensional coordinate of this. Similarly, if I apply this to faces and I learn just 2 dimensions, this network can't generate everything. It can't generate dogs and cars and space shuttles, but it can generate faces. And it can only generate faces within this space of the latent dimensionality, Z. And this is a 2-dimensional set of face variations. And it turns out that what the network is learning is along 1 dimension, it's learning whether the head is facing to the left or to the right. And along the other dimension, it's learning whether I'm frowning or I'm happy. Okay? So by diagonalizing the prior on Z, we're basically learning independent latent variables, and the different dimensions of Z encode interpretable factors of variation. And a good feature representation that can be computed using this encoder network from the pictures into the latent space images, so into the latent space vectors, is in fact capturing that aspect of the world. And the last component of this is that I can actually generate data. I can take the decoder and just vary the parameters and then generate images of faces, generate partial images of scenes, and so on and so forth. Okay? So what's really cool here is that we now have a decoder and we have an encoder, and we have a generative model of the world. We have an encoder that basically learns a latent representation of faces with features that are somewhat meaningful, and a generative model that allows us to decode that latent space and to vary that latent space through the prior distribution of the Z vectors. So to summarize, the variational autoencoders are a probabilistic spin of traditional autoencoders, and they allow generating data. They define an intractable density and then derive and optimize a variational lower bound of that density. The pro is that it's a principled approach to generative models, and it allows the inference of these latent space given X, which can be a very useful representation for all kinds of other tasks. And we're going to see that variational encoders and many other tools are in fact very often taking these learned representations as a sub-task that you can then use for all kinds of other things in machine learning. The cons is that it maximizes the lower bound of the likelihood, which is okay, but not as good as, explicitly evaluating this, such as pixel RNN and pixel CNN that you can look up. And the downside is the samples are in fact blurrier and lower quality compared to these generative adversarial networks. So as you can see, yes, the latent representation can vary and generate pictures that kind of look like different people, but these don't really look like real pictures. So just like our internal representation visualizations of these convolutional neural networks didn't quite look like real features of images, these are not quite real pictures of people. So we basically need to improve on the quality and the sharpness of the generated images. And again, there's a lot of active areas of research in variational encoders, looking for more flexible approximations, for richer approximate posteriors instead of just diagonal Gaussians. And there's Gaussian mixture models that are being used. And also, how do you incorporate structure in the latent variables? For example, how do you have distributions that are different for different categories, and so on and so forth. So what have we seen so far? We basically saw the concept of generation in the world as sampling from the latent space. And we saw how we can actually trick a non-supervised network into a supervised network by basically transforming our features, transforming our input images into some degenerate input data, and then predicting the original to learn these intermediate representations. And we also saw how even just using the untransformed X as the output, but forcing this intermediate position to be a lower dimensional latent space allows for, number one, compression, number two, learning of a meaningful internal representation, and number three, generation of additional data by sampling from this latent space. Okay, and then we saw how we can actually capture the parameter distributions through variational autoencoders, and how we can make these latent space parameters more meaningful by having them be orthogonal, or by having them be explicitly trained using particular categories of images, or making them tunable, and so on and so forth. And how these latent space parameters are in fact, in many cases, actually meaningful. All right, so let's see who feels that they've learned something so far. Very cool. So we're at 60, 35, 005. And then how is the pace so far? Okay, so 60% of the people feel it's just right. And then we have 40% slightly above, and then just one person on each end. So this is helpful. And lastly, who feels excited about what they've learned today? Is this a cool topic? Representation learning, generative model, being able to capture representations of the world, sample from those representations, generate images. Cool. If you're not excited yet, you will get a lot more excited soon. So we're at 50, 25, 25, 5. All right. So Jackie, I want you to organize a little stretch break once more.
Yes, I was preparing for this. I looked up stretches. Okay. Wow. Hi, everyone. Let's stand.
Very cool. All right. So the last topic for today is how do we actually improve the quality of the output images? We saw that this can be very powerful, but we saw also that the samples themselves can be very blurry. So what would be really awesome to have is a person that basically comes back and says, there's something wrong with this image. It's not quite right. Maybe you should fix this or you should fix that, and so on and so forth. But training such a person can be very expensive, and hiring the billions of humans that you would need to be able to train those images and train those classifiers that basically say, this image is no good, can be very, very slow. So maybe we should simplify the task. Maybe instead of saying, yes, you should fix that little patch over there because it's blurry, maybe we should tell the training system simply, yeah, no good, or yeah, good. Okay, so maybe we could have an army of people on Mechanical Turk providing feedback as to whether this image is a real person or a fake person, to try to get better at generating images of actual objects or people or rooms and so on and so forth. And that's what basically these generative adversarial networks are trying to do. So the adversarial part is that you're actually going to hire a person who's going to tell you whether you're wrong or not, and that's going to be your adversary. So you're going to be training your network to basically do better at predicting, at generating images of, fake people. And then you're going to hire an army of evaluators that are basically going to say, yeah, that's a real person or that's not a real person. But again, of course, as you guys have already know by reading the literature, is that instead of hiring an army of people, we're just going to train a deep learning neural network to do the task of evaluation. And we're going to get better at evaluating fake images, and we're going to get better at generating fake images simultaneously. And that's the adversarial nature of these networks. So they're generative because they're able to generate images. They're networks because they're deep neural networks, and they're adversarial because you're training, two networks against each other. One is going to be getting better at generating fake images, and the other one is going to get better at detecting fake images. So that's the key idea, and this was invented by Ian Goodfellow, who's actually the author of our book, and in NIPS 2014. So the concept of generative adversarial networks is that we want to sample from complex, high-dimensional training distribution, and there's no direct way of doing this. So the solution is going to be to sample from a simple distribution instead. For example, we're going to be sampling from random noise, and we're going to be learning transformations of these random noise into images from the natural world or images from a training class. So if I have a training class of every single face of every person on the planet, then any kind of sampling from random noise will generate only images that match that distribution. So we're going to be sampling from the training distribution using as input random noise to allow us to explore the space, not of all pixels in the world, but of all images of people in the world. So we can represent this complex transformation between random noise and a sample from our training set using, of course, a neural network. So we're going to have a generator network that is going to be constructing fake images from the generator. And then that's where the beauty comes in. Instead of hiring billions of people on Mechanical Turk, we're going to build a discriminator network that is going to get really good at distinguishing fake images generated by our generator network from real images from our training set. And it's going to be telling us whether something is real or fake. Okay. The beauty of all this is that it's still self-supervised. I didn't have to get anyone in there to go and hand label anything. I can just generate gazillions of images from a distribution. I can just gather gazillions of images of cars, and I can train a network to generate more images of these cars. So I guess, the training is the fact that I sort of put in gazillions of images of cars, okay? So the generator network is going to try to fool the discriminator by generating real-looking images, and the discriminator network is going to try to distinguish between real and fake images. Okay, so who's with me on the concept so far? So the concept of I'm going to have two networks pitted against each other, one trying to generate images from a distribution, and the other one trying to detect whether those images were real or fake. And it's going to basically have access to all of this as a way to make a decision of just real or fake, but no need to actually say what part of the image is incorrect or anything like that. This is a form of only weak supervised learning rather than sort of very detailed feedback. All right, so we're at 65, 25, 10, 0, 0. Okay, so let's dive right in. So we're going to train using effectively a mini-max game. The decoder, which is going to be, so the discriminator, which is going to be deciding whether the images are real or not, is going to try to maximize a function, and the generator is going to try to minimize that function. Okay, so the discriminator wants to maximize the objective of this function d of x so that it's close to 1 if the image is real, and that it's close to 0 if the image is fake. And the generator wants to minimize this objective such that this distance here is close to 1 if, in the opposite direction. So basically the discriminator is going to be outputting a likelihood of whether the image is real or not. So we're going to have basically this min and max. So we're going to be training this first through the discriminator, then through the generator, then back through the discriminator, then back through the generator. We're going to be training the different weights at the same time. So through this, we're going to be running the backprop all through the entire network or only through the discriminator. And again, we can clamp the weights of the discriminator and only train the generator, and we can clamp the weights of the generator and only train the discriminator to basically carry out this joint likelihood function of going through both the weights and the parameters of the generator and the discriminator. So then the expectation that we're going to be looking at is what is the distribution of x according to the input data. And it's going to be the log of this distance function applied to x. This is the discriminator output that is basically saying for real data x, what is that function? And then plus the distribution, the expectation of the encoded latent space given the distribution of that latent space with 1 minus the discriminator output for the generated results. So basically, z is going to be that random noise input vector, and then I'm going to be generating images from that random noise input vector given the weight parameters that I'm learning through the generator network. And I'm going to be using, the positive for the discriminator on real data, and then 1 minus that for the discriminator on the generated data. So what we want to have is the discriminator should be able to say that the score for any kind of image that was generated from the random noise should be 0. No, that's a fake image. And any kind of image generated from the actual input should be 1. So by having the min and the max here, and by having this 1 minus here, what we're effectively doing is one of them is trying to maximize the score for real images and minimize the score for fake images. And the other one is trying to do the exact opposite. Okay, so we have two things going on here. One is the discriminator output for generated fake data. The other one is the discriminator output for real data. And one of them, the discriminator, is trying to maximize that score. that basically is high for real data and low for fake data. And the generator is trying to minimize that score by actually trying to achieve the exact opposite. Okay, so who's with me so far on the objective function? So what we're trying to do is the generator and the discriminator have exactly opposite objectives on this exact opposite score. And the score is basically higher if you correctly classify real data as real, and lower if you classify fake data as real. And that's what is being used by the discriminator, but then the generator has exactly the opposite goal. All right, so we're at 45, 45, 8, and then 0, 0. Great. So it's basically a two-player game. We have a minimax objective function that is trying to sort of maximize these double scores, and then we're alternating between gradient ascent by maximizing on the discriminator and gradient descent by minimizing on the generator. So the gradient signal is basically, moving towards samples that are basically, when the sample is already very good, it's able to discriminate very, very well between them. And when the sample is likely to be fake, unfortunately, the training is kind of flat when you're looking at this. So that's a problem. That basically means that the training is actually going to be very, very slow. But you can use a trick, which is you can actually flip this aside, and instead of sort of doing gradient descent on the generator, you're doing a gradient ascent with a different objective function. And instead of minimizing the likelihood of discriminator being correct, we're going to maximize the likelihood of the discriminator being wrong. So we're going to be giving it samples that are way bogus. And because on the way bogus samples, it's now going to have a larger gradient, we're going to be able to actually train more rapidly. So basically, it's the same objective of fooling the discriminator, but now we're going to have higher gradient signal for bad samples, which actually works much better in practice. And that's usually the standard. So as an aside, jointly training two networks is very challenging and can be unstable. So choosing objectives with better loss landscapes can actually help the training. And that's an active area of research. And in fact, some of the most powerful GANs nowadays are starting with very low resolution images. So 4x4 pixels, then 8x8 pixels, then 16x16 pixels, and so, etc. So progressively increasing the resolution to get that stability of training, rather than sort of starting with full resolution images. And then, the network can be very unstable at the beginning. You start with very low resolution and you sort of move into a space of both generator and discriminator that are well behaved. And then you're sort of, scaling further through that through that space. All right. So, the GAN training algorithm is for some training iterations, and for some steps, you're going to be sampling a mini batch of M noise samples, Z, from the noise prior. So I'm going to sample random noise, and I'm going to generate examples from the actual input data. And then we're going to update the discriminator by ascending the stochastic gradient relative to the parameters of the model of the discriminator. And then afterwards, update the parameters of the generator. The discriminator is trained using the full network. So basically using both the generator that generates those images and the parameters here. But now I'm clamping the parameters of the generator because I'm only optimizing the parameters of the discriminator. So I'm taking the gradient relative to the parameters of the discriminator and then doing backprop through that. And then we're going to be sampling a mini batch of noise samples from the noise prior, and then updating the generator by ascending the stochastic gradient using that improved objective. And then now I'm not going to worry at all about the discriminator. If I clamp that, the gradient doesn't care about the discriminator because now it's the gradient relative to the parameters of the generator. So then I'm only going through the theta of the parameters of the generator, generating images from the random noise, and then discriminating these images using a fixed set of parameters for my discriminator. So I'm basically alternating between training the discriminator through the generated images, and then training the generator through, again, the discriminator being fixed for those images. Okay, so let's see who's with me on the two steps here. First, clamping the generator, and then taking the derivative relative to the discriminator, and then clamping the discriminator, and then taking the derivative through the generator parameters. This is lovely. So 44, 28, 24, 04. So after the training, now we can have some fun, because we've basically trained the generator network to generate awesome real world looking like images and discriminate them from, actual, and a discriminator that's trying to distinguish them. If the discriminator is getting better and better, and the generator is getting better and better, then at some point they're going to surpass human performance, and they're going to be able to, sort of generate amazingly good images. So again, if you were just looking at mean squared error rather than having an actual discriminator function, then, if you were to clamp down the features of an encoder for that image, it would basically erase this ping pong ball from this image, because the error is relatively small. But if the discriminator is able to tell that the ball is missing, then the GAN is actually going to do a much better job than any kind of mean squared error. Similarly, mean squared error would say, oh, well, this is a fine image because on average the errors are not so bad, but it's missing altogether, and it's missing a lot of sharpness here that the discriminator network is able to detect. And that's the beauty of what we're doing here, the fact that this discriminator can start paying attention to details that are extremely precise, easy to detect if you train a neural network to do so, but totally invisible to mean squared error. And the samples that you're getting are in fact never exactly the same as your initial data. So if you look at the nearest neighbor from the training set for any of these images, they're not quite exactly the same. They're always slightly different. And that basically tells you that the model hasn't overfit. And again, you can see here the nearest neighbor examples. So again, that's the beginning of a long journey that has happened over the last few years. GANs feel like ancient history, like 7 years ago, and they have really transformed the world, but a lot has happened in that space. The first is simply coupling GANs with these convolution architectures. So basically right now, the GAN model doesn't actually have this representation learning hierarchical structure that you have from convolutional neural networks. So coupling them with convolution architectures can basically give you a lot more power. So the generator can be an upsampling network with fractionally strided convolutions, and the discriminator can simply be a convolutional neural network. So the architecture for a deep convolutional GAN is to replace any kind of pooling layers with strided convolutions and fractional strided convolutions, which allow you to do gradient descent through them much more naturally. To use batch norm in both the generator and the discriminator, to remove the fully connected hidden layers for the deeper architectures, because who cares? This is not about representation learning. The fully connected is simply for a training task, not for representations. And what you really care about is representation learning. And then to use ReLU in the generator for all layers except for the output, which then uses TANH, and then use a leaky ReLU in the discriminator for all layers to basically make training through that more natural. So you can basically build these convolutional architectures that allow you to, learn thousands of 4x4 features, hundreds of 8x8 features, hundreds of 16x16 features, and so on and so forth, effectively learning representations at all levels trained through this network. And here's some samples from the model. So when you train your generative adversarial network using these convolutional architectures for rooms, you can basically generate rooms that are architecturally plausible. And you can basically now go back to the latent space coordinates of your images. You can basically say, what is the latent space coordinate of this image? What is the latent space coordinate of that image? That gives me a set of vectors, a set of scalars. And I can now interpolate between these scalars and transform this room into that room. and transform that into this, and so on and so forth. And you can see that that transformation is effectively generating realistic looking rooms at all levels. So if you were just trying to, morph the old fashioned way, this into that, you would go through intermediates that make no sense. But what you can see here is that all of these are, good looking rooms in their own right. So again, you can sample from the model and add variation that allows you to, add, for example, sunglasses that were learned on men, but on women's faces by taking the sunglass man, removing the no glass man, and then adding the vectors of no glass women. Again, these are very old images, but this is basically telling you that the network is effectively learning in this latent Z space representations that actually make sense, from the real world. So again, you can Google Ganzu, and then you can see all of the different generative adversarial network models that have been created, and this list is growing. There's been a lot of work in better training and generation, and you can sort of see a lot of improvements in those. There's progressive GANs that I mentioned earlier, where you can learn first a 4x4 image and an 8x8, 16x16, and progressively add resolution, effectively leading to these incredibly well-trained generator and discriminator networks that are, generating these, this person does not exist images that you've probably all heard about. You can also have domain knowledge transfer. For example, in your input, you could have horses, and in your output, you could have the zebra vector, and then you can sort of transform back and forth between them. We don't like comparing apples and oranges, but this can actually transform apples to oranges and oranges to apples. You can actually upscale images. You can, take a camera image where everything's in focus, and then learn images that you would get from a fancier camera. You can change the winter vector into a summer vector from a scene, and then transform, summer into winter at Yosemite. You can take descriptions and then change the text to generate images from those descriptions that are matching, again, that latent space vector. Simply change the parameters of that latent space. You could basically sketch out, terrible sketch of a bag, and then fill it in with textures that you have now sampled from the latent space of bag images. So the only way that your network knows how to create this, terrible sketch is by sampling from the representations of bags. It doesn't know how to make things that don't look like bags. So whatever the latent space closest match to this hand sketch is, it's going to generate through the generator an image of an actual bag. Or you can take, map and transform it into a satellite image by learning what satellite image would be sampled from according to this latent representation projection of this map. And, it has gone a long, long way since. So NVIDIA, for example, has generated this, this person does not exist website that allows you to now sample from those. And what they've done is sort of replace this traditional architecture with simply a large number of these parameter spaces that is now explicitly learning these orthogonal parameters that allow you to now decompose different components of that image. So this is their standard image. This is the average person on the planet from images that they have trained. And you can basically take any person, change the parameters from that latent space to the average person, and then change it further to the opposite of that person. So you can basically take, this person, transform it through the average person and back to the, latent space representation opposite of that person, which happens to be another perfectly normal looking person, but in that latent space representation is exactly the opposite of this person. And same for this, you can take that person and have the exact opposite in latent space. You see this person looking to the left and wearing glasses, looking to the right and not wearing glasses, slightly older man, slightly younger woman, et cetera, et cetera, et cetera. And same for this, you can basically apply different kind of dimensionalities along the style space for each of the different types of features. So basically, if you have a course style from one source, so basically we're now generating images. So we're taking the image of this person and then applying the style of that person here. So if I'm transforming each of these people in the style of this person, then you can see the glasses from here applied there and the man vector from here applied there, even though the core styles are coming from that image. And you can see these sort of two-dimensional representations, which are truly, truly stunning. It basically says that you have truly learned a latent space vector that is representing something that is absolutely meaningful about the world. And the network can't generate a bad image. It's just unable to. Whatever input Z vector you feed it, the output X image is going to be very, very good looking. So the sky is the limit after all that. So I just want to give you a taxonomy of generative models from this. So you can basically have explicitly modeled density functions or implicitly modeled density functions. And what the generative adversarial networks are doing is not explicitly modeling that density the same way that the variational autoencoders do, but are implicitly modeling this by coupling this generator and this discriminator networks together. And you can have Markov chains from that implicit density instead of having directly modeling that density. You can actually have a Markov chain walking through that. For the explicit density model, you can actually have a tractable density function that you can actually explicitly compute. And there's many models for that. There are fully visible belief networks. Or you can approximate that density through a variational method or a Markov chain method. So I encourage you to explore all of these different architectures. And lastly, unfortunately, we're out of time, but Ben Lingerish, who's actually here on the Zoom, has done some beautiful work on mapping GANs and VAEs, in fact, showing that the two models are equivalent. So we might actually have him as a guest lecturer tomorrow at the recitation. But what I want to leave you with is the concept that the power of deep learning doesn't come from the X and the Y or the fully connected layer. The power of deep learning really comes from the latent space representation learning. And the classification tasks that made deep learning so popular and sort of made people realize just how amazingly powerful it is was just an excuse to really get into the representation learning paradigm. With that paradigm, we can change X that has no Ys. We can take unlabeled data and mix and match tasks. And there are many, many ideas that are possible. But the message that I really want all of you guys to get is that your ideas could be even better. This is a very young field. This is not like we're learning stuff from, particle physics or turn of the century Newtonian or relativistic models that have been decades in the making. No, this is 5 years old. This is incredibly young in the grand scheme of things. So I really want you to just let it all loose and be creative with your models, experiment. There's so many open architectures out there, so many models where you can mix and match and create all of these incredibly novel tasks. And the concept of I'm going to rotate an image and predict the correct orientation sounds trivial, but it was a major advance because the only way to do that is to actually learn meaningful latent representations of the world. So there's many pretext tasks that have been invented, predicting the self, predicting before and after, missing patches, fill in, correctly rotating, colorizing, upsampling, multimodal learning. We saw autoencoders that can basically simply clamp down the self-prediction task through a lower dimensional latent space. And we saw how beautifully these can apply to either faces or to MNIST characters, handwritten digits. We saw how you can actually capture not just the mean, but also the variance of these autoencoders and be able to sample from a distribution of latent spaces and images to basically create not just one solution, but a space of solutions, which is the first step to having a truly generative model of the world, where you can sample from a true underlying distribution of the latent space parameters to get images that are capturing the diversity of images in the real world, rather than the enormous space of possible pixels, which is huge and completely uninformative. It's really the much smaller space of faces or boats or living rooms and so on and so forth. How we can make those latent space parameters meaningful by making the variational autoencoders constrained to be orthogonal in their space vectors, to basically have the dimensions of the latent spaces be as distinct from each other, and make them explicit, make them tunable. And then how we can actually forego the representation altogether, and instead of having an explicit representation of the density function, learn that implicitly through a second network. So basically train this using a second network that basically tells you whether something is real or not real. And we saw how that dramatically improved the quality of the output images compared to the variational autoencoders, to basically now have images that are indistinguishable from real people, all sampled from a latent space that now has dimensions associated with meaningful things like man, woman, old, young, glasses, no glasses, et cetera, et cetera, et cetera. So that latent space representation is truly capturing knowledge about the world. It's truly capturing intuitions that really, truly make sense. Last point I want to make is the sky's the limit. The field is so young, and we now are going to have a series of lectures on the application domain of life sciences, but this is applicable anywhere. So stay tuned. This is going to get a lot more fun. So see you guys tomorrow for recitation, and the TAs, please stick around, and Ben, please stick around. But everyone else, tomorrow, and we're going to have first a recitation and mentoring session. We might use GatherTown for the mentoring session to have people go through different rooms. We're going to try to maximize the usefulness here. We need a discriminator network to basically tell us if we're doing well or not. But without that, we're going to try various different iterations. All right. Thanks, everyone.
Hey, Manolis.